Joshua Tumwine. So we're going to be building the states of matter from where Mr. Patum had stopped last time. So this time we're going much into chemistry, or the depths of chemistry, and I'll explain a few issues and try to elaborate what Mr. Patum was trying to look at last time. Our numbers are already there. If you are to enroll, you let us know and we shall put you on the program. So that is one. We have those 3 contacts. You call and at least one person is going to be available to pick you and you can enroll your child. So that's me. My name is Joshua, like I've already said, and allow me to take you through the presentation. Matter is anything that occupies space and also has weight. So those are the 2 key issues that we should always understand. So instead of even saying weight, you can call it mass, that occupies space and has mass. So states of matter. We have many states of matter, and many, of course, we've always been used to solids, liquids, and gases, but we're going to look at also the plasma as a state of matter. So let's look at solids. The characteristics of solids include they have, of course, a fixed volume, they have a fixed shape, we know that so well. They are incompressible because the particles are already very close, so they cannot get closer further. It is impossible. They do not flow, unlike the gases and liquids which flow. They have a definite shape. You can tell that that is a particular solid. If it is a pure solid, you can easily tell that this is maybe stone, this is something. You can easily see the shape. It might be irregular, but at least it has a shape. The particles are closely and regularly packed together. We've already said that just because they have very strong forces of attraction. Usually, at certain temperatures, the regular arrangement of particles in the solid breaks down, and this particular point we say that the solid has melted, so it will turn into the liquid state. So the temperature is also called, in that particular case, the melting point. Let's look at now liquids. Let's look at the classics of liquids. 1, they have got a fixed volume, we know that so well, but they don't have a fixed shape, and that's why they usually attain that particular shape of the container. Like we are saying, they take the shape of the container. They are incompressible also because particles are still close, though not very close like those ones of the solid. They flow easily, so if you pour it one particular point, it can flow to the other freely. They have a definite volume, so those words I'm underlining are the key words of the they take up, of course, the shape of the container, like we've already said. If you get water and put it in a glass or milk or anything, then you'll be able to see the shape of that particular container, but not particularly the shape of the water or the milk. Liquids cannot be compressed by squeezing, and that one I think it was talked about last time when we say that you have a syringe, for example, and then you draw in air and hold on top of the syringe and then try to press. the piston can move inwards, showing that air is compressible. But when you put in any liquid, you cannot place that piston and it moves inwards. It is impossible. That's what we are talking about, that liquids cannot easily be compressed. Okay? When liquids are heated, their particles are excited and therefore they move very fast, and finally they will turn into gas by the process of evaporation. So the temperature at which this one happens is usually called the boiling point. So if you look at an example, the boiling point of pure water, I want to be very specific, pure water. So this is pure water is a key word. Pure water is always 100 degrees Celsius. Let's look at now gases. For the gases, we expect that they have their own characteristics. They don't have a fixed volume, like unlike the solids and the liquids. They don't have a particular shape. For them, they are compressible. We said that one sometime back when we were trying to look at general characteristics in real life of these particular gases. They flow in all directions just because of weaker forces of attraction between the molecules. For them, they have no definite shape and they don't have a definite volume. I've already said that. The particles cannot attract each other and therefore can be compressed. Now, when these gases are cooled, they usually turn into liquids, and this process is called condensation. So we should know that the process by which liquids turn into liquids, by which gases turn into liquids, is what we call condensation. The behavior of particles in solids, you should know, liquids and also gases is governed by the principle that we call the kinetic theory of gases. The statement, and let's try to look at it also. But before we can go for the kinetic theory of gases, let's look at change of state. Change of state, we've already said, is brought about by changes in temperature. Okay? If, for example, a liquid is cooled at very low temperatures, it will change to the solid. That is, for example, changing water to ice. So we are having our diagram there, and we know very well that if you're changing from solids to liquids, then that is what we call melting. But then if you're changing backwards and you're moving from liquids to solids, that's where we are going to be having our freezing. So you're trying to change from liquids to solids. Then when you're changing from liquids to gases, in that case you're going to have what we call evaporation. And when you're changing backwards from gases now to liquids, we've already said, and then in that case we shall be having what we call condensation. That's how condensation. Now gases can also change to solids directly without passing through liquids, and they can also change back from solids to gases still without the melting. That's the process that we call sublimation. So I hope that one is very clear and we don't have to debate about that. So what does this mean? It means that sublimation is a process by which a solid can easily change to a gas, but without passing through the liquid phase, without passing through the liquid phase, that is when it is heated. Substances which subbrine are so many. We have like the iodine crystals, which I think is the commonest. Iodine crystals, they're usually crystals. We have ammonium chloride, we have solid carbon dioxide, we have quite many. We have solid carbon dioxide that we call dry ice. I think everybody knows that. We have aluminum chloride, which is supposed to be anhydrous, and we have also anhydrous iron 3 chloride. Even sulfur, naphthalene, and many others can subbrine, but we can just use those as examples. So if someone asks you a question that give us examples of those substances which subbrine, we have one here, which is iodine. We have ammonium chloride, number 2. Then we have solid carbon dioxide, which you can take as number 3. We have anhydrous aluminum chloride, is our number 4. And then we have number 5, which is an 3 chloride. Note, water exists in 3 states, which you already know. That is, solid state is called ice, but then the liquid state for it is called water, we know very well, and that's the state which it exists in at room temperature. But then the gaseous state of water is either called water vapor or steam. So we've already said that at room temperature water is always in liquid state. So when you look at this particular tentative diagram, we are trying to look at the particles. These ones which are highly packed are those of a solid, and these ones which are packed but not that much packed, they are for the liquid. Then these which are spaced, which can easily flow freely, they are for a gas. Everybody knows that. Let's look at differences in the particles of the solids, liquids, and also gases. While those in liquid are packed close together in an orderly arrangement, those of liquids are packed together but not in an orderly arrangement. And then when you look at the ones for the gas, for them they are random. They are not even packed together, they are random, just move freely. There is little space between them for the solids, little space but less than more than that of solids. Then here we have a lot of space between the particles. Those of the solid move by vibration. They don't move from point to point, so they move in one fixed position. But those of the liquid can move freely throughout the liquid, and those of a gas also move freely within the gas phase. Let's look at the differences between matter itself and its particles. Matter can be colored. For example, if you look at sulfur, everybody knows that sulfur is yellow, and because for it is yellow, it doesn't mean that its particles are yellow, so that one does not qualify to be having particles of the same color. No. When you look at particles, for them they are not colored. Substances feel hot or cold, but the air particles do not get cold or hot. You should know that also. So the temperature is due to the speed of movement of particles. Okay, if the particles are moving very fast, then we expect the temperature to be high. Alright, so matter expands when heated, but particles do not. You know that? So they increase the distance between particles during expansion. Changes of state, we've already looked at them, we don't need to waste a lot of time on that. So we said melting is a change from solid to liquid, which breaks the forces of attraction holding the particles together. The temperature at which it melts is called the melting point. Let's look at heating and cooling curves, and I want us to pay attention here. A heating curve is a curve of temperature against time. Temperature against time here. And you should know that if you have a solid, for example, from this particular point, this point, we have a solid, and then you're choosing to increase its temperature. Let's say this is say from T1, this is our T1, to say T2. It will reach a point and then the solid starts to melt. When the solid starts to melt, the temperature will remain at T2 until when all the solid has turned into the gas. So at this particular point we have, sorry, liquid. At this particular point we shall be having a liquid phase. So between this B point and then this particular point, which is supposed to be C here, we are having a solid and a liquid, both of them existing in equilibrium. Then if in the liquid, now the temperature is going to increase, for example, now to increase from T2, and then it moves up to around this point. Let me just try to draw to show you what I'm trying to mean. This point, let's assume this is now T3. So, and when it reaches T3, it will start, the liquid will start changing to gas, and it will remain in gas liquid equilibrium until when all the liquid has turned into gas at this point. Then we expect this gas to take up as much temperature as you want. For it can take more temperatures, it will not have any limit, because from the gas state we are going nowhere. So that's what we call the heating curve. If you are trying to melt and move on, or if you're trying to boil the water and move on. Now when you look at T2 here, in this case it's going to be assigned the melting point, because we are having the solid forming the what? The liquid. Then when you go to T3, in that particular case, looking at the heating curve, then this is going to be our boiling point. Boiling point. Now, if this substance, for example, is water, we shall be expecting this T2 to be 0 degrees Celsius. Then we shall be expecting the T3 to be 100 degrees Celsius. Now, let's use the same curve to look at what we call the cooling curve. So the cooling curve is all about having maybe vapor, and it is turned to a solid in the end. What happens is, now for it starts from this side, it's just going to be sloping. We are having a gas phase, for example, like that. So this is our gas here, gas phase. Then to reach the point, and this gas of course starts forming a liquid, and that's what we call the condensation. So this particular point we expect a liquid, and of course gas existing in equilibrium here. And then when we reach a particular point, we expect now everything turn into a liquid. So we have a liquid, for example, that moves now like this, and to also reach a point whereby the liquid will start turning into a solid. Let's say this is the particular point. Until when all the liquid has turned into the solid, the temperature does not change. That's why we have in this particular constant. Then when you move, you'll be having a solid, and the solid can take up as much, you can lose as much heat as possible, and you find it's going to be negatives up to absolute zero. Now, if I'm to compare now this particular curve, this is called the cooling curve. Okay, but then this one that I'm having here is called the heating curve. So for the cooling curve, this particular point, which was the boiling point, is going to be the condensation point. Then this particular point will be, of course, the freezing point. So you read off from the other side and you find the freezing point. So you can ask you about the timing that took for the whatever to happen. You just have to draw these lines and then you'll be able to read on the time, which is always in seconds, like that. That's what we call the heating curve and also the cooling curve. From the graph, of course, I don't want to waste time on that because I've already explained what I was saying. Between A and B, temperature of the solid increases to the melting point. BC remains constant. Heat is absorbed to break the forces of attraction instead for raising temperature. Solids and liquids are present at BC. CD, all those things I've already talked about them, so we don't need to waste time in that particular case. You just have to read through and you'll be able to get what I'm trying to mean. Okay. What is freezing? The change of liquid to solid by cooling down the liquid. Freezing point, the temperature at which the liquid does what? Freezes. If you're moving like this on this particular graph, like you're seeing me moving, then this one is going to be called, for example, instead of melting point, it's also called the freezing point, because now you're doing what? You're cooling. This curve which is moving like this is the cooling curve. Okay, and if this one was, if this one, for example, was the gas, you should know, and then someone is telling that now this gas formed here a solid, I'm just assuming, then the process that happened between A and B is no longer freezing, is no longer melting, but it is called sublimation, because we are having a direct change without passing through the liquids and in any case from the liquids, like that. Alright, so all those things, I think you're seeing what I'm trying to mean. Just take your time and read through. Do not have any confusion. What is boiling? Boiling, the change of liquid to gas by absorbing heat to break the forces holding them together. So the boiling point is the temperature at which the liquid boils. Now evaporation is a little bit different, you should know. For it, it is a change of liquid to gas. It doesn't matter what happens. It can happen even below the boiling point, so it can happen at any particular point, which is usually slightly even above the room temperature, for example for water. Okay. Condensation, change of states from gas to liquids, done. Sublimation, I think we've already talked about it, don't need to waste time on that. Let's look at kinetic theory of matter. Kinetic theory of matter. And look at this. The word kinetic comes from movement. So we're trying to look at the movement of particles of matter, but in a theory form. What does it state? Matter contains, first of all, small and they are invisible particles that are usually in constant random motion. That's the statement. So kinetic theory assumes that particles are really too small to be seen directly with our own eyes. There are spaces between them, and the amount of space varies between each state. So for the solids, gases and liquids, they have different spaces in between the molecules or the particles in that case. We've already said that particles are always moving, and they move in different speeds for different states. Mhm. Evidence for existence of particles in matter. We are having two. One is called Brownian motion, and the second one is called diffusion. So diffusion is the spreading and mixing of particles in gases, and of course, so that's what we're trying to look at. But you can also say the movement of particles from where they are highly concentrated to where they are lowly concentrated. That's what we call diffusion. So diffusion of gases. We start with the diffusion of gases. Assume you're having bromine drops and you put them in a particular jar, and then you put a cardboard on top and then put another jar which is empty on top. Then you slightly remove the cardboard so that the jars combine together. What do you think you're going to observe? You realize that the bromine evaporates, and then it's going to be not only covering the first jar down, but it will cover the whole jar. So it is always trying to move from where it is highly concentrated, which is the first jar, and then it is going to the low where it is lowly concentrated, which is the second jar, until when equilibrium has been established. Diffusion will not stop. Let's explain. Bromine particles move from the lower jar to space and then into the upper jar. So at the same time, air particles move down from the upper jar to mix with the bromine particles in the lower jar. Eventually, bromine and air particles are mixed up completely. That's what I'm just trying to look at. If you look at this particular diagram, that's what I was trying to talk about. This is our cover, which can be a cardboard, but here you put just bromine liquid. It will start evaporating. Sorry. When you remove this particular cardboard here, then this is what we're going to be having. In the end, everything is going to be uniform because bromine is reddish brown. So you'll find it. Well, these are two jars. If you look at this particular point, that's why they should be separating, and you'll find that everything now is filled with this particular same bromine. Okay. Diffusion of liquids. You can use copper 2 sulfate, please. This is called copper. Yes, you just be patient. Copper 2. It is written like that. Then we have sulfate. Sulfate like that, and then of course this one, let me just try to be very clear. It's supposed to be capital C, small u, and then S O, all of them capital, but then the K4 is this small. That is copper 2 sulfate. So copper 2 sulfate crystals pressed in a beaker of water. We see the blue particles, sorry, the blue color of this particular copper 2 sulfate spreading throughout the water, making the whole solution now blue. That's what I'm trying to look at. This one is the original copper 2 sulfate crystal, but now in the end, everything has turned to blue. You can see the whole of this is now what? Blue. Okay, so let's look at the factors which affect the rate of diffusion. The factors, we have temperature. The higher the temperature, the more the particles absorb energy, making them move faster, or in other words, we say it increases the kinetic energy of particles, making them move very fast, and therefore the rate of diffusion also does what? Increases. And the lower the temperature, then the slower the rate of diffusion. We have also mass of particles. The greater the mass, the slower it diffuses. The smaller the mass, the faster it diffuses. You don't need to waste time on that. And you know what I'm trying to mean. Concentration. If you're having a high concentration, then you'll be having very many or more particles which can diffuse at a given time. So the higher the concentration of the diffusing particles, automatically the higher the diffusion. And the lower the concentration, the lower the diffusion. Let's look at an example of diffusion in gases. if you're, for example, provided with an open-ended glass tube, and at one point, this is a particular point we are looking at, let's call it, for example, A, point A, you cock up cotton wool soaked in concentrated ammonia, and then you say maybe point B, the other opposite end, and then you get cotton wool soaked in concentrated hydrochloric acid. And you leave this particular experiment to stand for some good time. In the end, you're going to find the white ring forming around here, and that white ring is going to be of ammonium chloride, just because the particles of ammonia which are produced from ammonia solution will come and combine with those of hydrogen chloride, which is got from hydrochloric acid. So we shall be having the white particles here, or the white ring forming around this particular point. Let's call it X. Now, what is surprising is when you look at the distance from A to X, it's going to be longer distance than the one which is from B to the same point of X. This one is going to be shorter, and this is because particles move at different rates. So it means that now the particles which I got from HCl are heavy, but then the ones which I got from ammonia solution are very, very light, so they move very fast. So by the time the particles move from B to X, then those ones of A will have already moved from A to X with a longer distance, so they will meet at that particular point, which is X, like that. So we just repeat ourselves: cotton wool soaked in aqueous ammonia, which must be considered, and another soaked in HCl are placed on opposite sides of the tube. Ammonium hydroxide vapor, which is ammonia gas, and hydrogen chloride vapor diffuses in the tube, and the compound produced inside the tube closer to HCl soaked particles, which are heavier. So the greater the mass, of course, the slower the particles diffuse, and the smaller the mass, the faster the particles diffuse. An example. No, this one, just ignore. This was supposed to be for the last bit. Let's look at chemical and physical changes. What is a chemical change? Chemical change is a process that occurs and a new substance is formed which cannot be reversed. For example, we know many: rusting, explosion, burning, all those ones are the so-called chemical changes, already taught in primary. Burning of paper to ash, and others. Our physical change for it is a change in which no new substance is formed, and the change is reversible. So you can reverse it. If I have melted, for example, water, let's say that is ice to water, I can again form ice with the same particles, e.g. freezing, like that, evaporation of water, magnetization of iron, all those ones, sublimation of solid iodine, and many, many others. Okay, differences between the physical and chemical changes. So we have one: no new substances, like we already said, formed, that is for the physical change, but then we always have a new substance for the chemical change. The change is reversible for the physical change, but then the change is irreversible for the chemical change. There is no energy in form of heat or light absorbed or released during the reaction, but then for the chemical change there is always energy. You should expect energy in form of light or heat, or both. There is no change in mass, not at all, when there is change in mass, because you're forming something new. So you can use mice actually to recall. Also, this is a mnemonic in the real sense, to recall those ones. So M for mass, I for irreversible, S for the new substance, or no new substance, so substance, and then E for energy, like that. So it can help you at least recall all those four differences between physical changes and chemical changes. Finished. Let's look at solutions, crystals, compounds, and mixtures. Solutions. A solution is a uniform mixture of two or more substances. When you add sugar into water and you stir it, the sugar dissolves in water. You will not see it again, so it forms a solution. So in this process, sugar is a solute, and then water is acting as a solvent. Okay, so we have those two substances, and a mixture of sugar and water in that case is going to be called a solution. Then now, what is a solute? A solute is a substance which dissolves in a solvent. So a solute is a dissolved substance in a solution. So solvent, for it, is a substance which dissolves a solute. You know that very well. We even have examples, and they are there: water, ethanol, petrol, and others. Types of solutions. Saturated solution. What is a saturated solution? A solution which cannot dissolve any more solute at a given temperature in presence of undissolved solute. So once you add a lot of sugar in just a little water, it reaches a point whereby it will not dissolve. So in that case, it has formed what we call a saturated solution. So this particular undissolved solute is the so-called excess sugar that I'm talking about. But then we have what we call a supersaturated solution. For it is a solution which contains more solute than it can hold at a particular temperature. So most times, even these particular saturated solutions, if you increase the temperature, much more of the solute will dissolve. But if you cool the temperatures back, then you see it precipitating out the crystals. So a supersaturated solution is a particular solution which can contain more than it can hold at a particular temperature. Suspension. A liquid containing small particles of a solid which are spread throughout it and usually settle on standing. Take an example: if you get chalk and put it in water, or maybe when you get dust, when you get charcoal dust and put it in water, in the end you'll find when it has actually sunk, it will settle. That's what we call the suspension. Differences between a solution and a suspension. Suspension contains solid particles which can be seen, but then the solution has no solid particles. That's number one. Okay. In a suspension, the mixture can be separated by filtration because we can see the particles, but then the solution, you cannot separate anything. So in a suspension also, the solid particles settle on standing, but then the solution has no solids that can settle on standing. Formation of crystals. What is a crystal? A crystal, number one, is a solid. There is no crystal which is a liquid that has solidified into regular fixed shape. So they have regular shapes. They usually have flat surfaces and sharp edges, and they are really shiny because of high refractive index. Crystals are formed when hot solutions of salts are saturated and cooled down. So you see crystals forming. But now what is surprising is that the size of the crystal depends on the original crystal maybe that you've just added. So if you want a big crystal, you get a crystal of the same nature and you add it into the saturated solution, and then you start cooling. You always form the crystals of the same size. That's how even sugar is made. If you want sugar with bigger crystals, you make one crystal of sugar which is big, and then you just drop it in the solution, and then you allow to cool. It will crystallize, forming bigger crystals of sugar. Substances which form crystals are called crystalline substances. For example, sodium chlorides, copper 2 sulfate, but some solids don't form crystals like charcoal or glass or metals. We don't have anything like that. So for them they are called non-crystalline substances. How do you grow a large crystal? I think I've already talked about that. You fill a beaker with a solution of copper 2 sulfate, say, and then you get one good big crystal and tie a thin thread around. Hang it in a solution and press a beaker in a warm place for several days. The crystal grows large, and as the solvent slowly evaporates. Let's look at water of crystallization. Water of crystallization. So some substances can have what we call water of crystallization. For example, copper 2 sulfate. Copper 2 sulfate is always having 5 molecules of water, and we usually call them hydrated substances in that case. So it is called hydrated copper 2 sulfate. But then when it loses that particular water, it becomes what we call anhydrous copper 2 sulfate. What is water of crystallization? It is the definite amount of water some substances chemically combine with when they form crystals from their solutions in water. A crystalline substance that contains water of crystallization is said to be hydrated, like I've already said. Not all substances can have a specific amount of water, so we have those special substances which can have, and they are called the crystalline substances, and they are hydrated. Okay. Examples: we've already said we have copper 2 sulfate, we have iron 2 sulfate, sodium carbonate. No, this one is supposed to be sodium carbonate. This is C or 3. This one is a 3. So this one, let me just remove my foot. This is sodium carbonate. Sodium carbonate. Looks like that, but still with 10 water. So this one is still part and a dot. However, also sodium sulfate, which is the formula that is here, is also part of those crystals. So there are many, cannot exhaust. Some substances do not contain water of crystallization and are said to be anhydrous. So I think you're getting what I'm trying to mean. Once it loses, then it is said to be anhydrous. Okay, we have potassium nitrate and many others. When hydrated substance is heated, it loses water of crystallization. For example, copper 2 sulfate, it can lose water of crystallization, and then it forms for you anhydrous copper 2 sulfate. So there we are. You see, and that's what we have. When it is a crystal, it is always blue. Then when it is anhydrous, it is always white. This is white.